After nearly a month of silence, the mysterious interstellar comet 3I Atlas, nicknamed the interstellar ship, may have reappeared in the sky. On Sunday night, several telescopes detected a faint glow in the region of space where the comet was predicted to be. The detection came as a surprise to many in the astronomical community who had begun to wonder whether the object had fragmented during its close approach to the Sun, or whether it had simply become too faint to observe with current instrumentation. The initial signals were weak, barely registering above the noise threshold of the detection systems, yet they were persistent enough to warrant immediate follow-up observations from multiple facilities around the globe. Teams in Chile, Hawaii, and the Canary Islands quickly redirected their instruments toward the coordinates, hoping to confirm what could be one of the most significant astronomical observations of the decade. But the data are puzzling. The object behaves strangely. Its brightness fluctuates rhythmically, as if someone were turning a light on and off. Some experts cautiously suggest it could be sunlight reflecting off a large metallic surface. Others suspect an instrumental glitch, yet the timing seems too precise to be mere coincidence. The periodicity of the fluctuations is remarkably consistent, occurring at intervals that some observers have measured at approximately 7.3 hours, though this figure remains preliminary and subject to verification. What makes this particularly intriguing is that such a regular pattern would suggest either a rotating body with an extremely asymmetric shape or surface composition, or something far more extraordinary that few scientists are willing to discuss publicly at this early stage. The brightness variations are not subtle either. They range from barely detectable to roughly 3 times brighter at peak, a variation that far exceeds what would typically be expected from a natural cometary nucleus tumbling through space. "We're not just seeing a comet. Its movement is too smooth, almost controlled," said one researcher from the Atlas project, who asked to remain anonymous. According to him, the latest spectral readings indicate an unusually even reflection, something not typical for natural celestial bodies. The researcher, who has been with the project for over a decade and has observed countless comets, asteroids, and other small bodies, expressed a mixture of excitement and bewilderment at what the data seem to suggest. In a private communication that was later leaked to several science journalists, he wrote that the trajectory of 3I Atlas shows micro-corrections that are difficult to explain through conventional gravitational dynamics or outgassing effects. While comets often exhibit non-gravitational accelerations due to the rocket effect of sublimating ices, the pattern observed here is different. More systematic, more deliberate in appearance, though he was quick to add that this could still be the result of complex rotational states interacting with asymmetric outgassing. The spectral data, meanwhile, show an absorption pattern that doesn't quite match any known cometary composition. There are the expected signatures of water ice and various organic compounds, but there are also unusual reflectance peaks in the infrared that some have speculatively associated with processed metals or ceramics, though such interpretations remain highly controversial and are dismissed by most mainstream researchers as premature and sensationalistic. Among astronomers, echoes of ancient myths are beginning to resurface, tales of celestial messengers returning from the void with news from other worlds. In some circles, 3I Atlas is already being called the Herald of the Void, its reappearance viewed not only as a scientific event, but as a symbolic one, a return after disappearing in the fire of the sun. This poetic interpretation has gained traction, particularly among amateur astronomers and science communicators, who see in this object a bridge between humanity's age-old fascination with the heavens and our modern scientific understanding of the cosmos. Throughout human history, comets have been viewed with a mixture of awe and terror, seen as omens of great change, harbingers of disaster, or messengers from the gods. The ancient Chinese kept meticulous records of cometary appearances, associating them with the rise and fall of dynasties. The Romans saw them as portents of death for emperors and kings. In medieval Europe, the appearance of a great comet might signal plague, war, or famine. Even in more recent centuries, before the scientific revolution fully dispelled such notions, comets held a special place in the human imagination. Objects that seemed to defy the orderly clockwork of the celestial spheres, wandering across the sky with their own mysterious purpose. Now, with 3-Eye Atlas, we have something even more exotic. A visitor, not from the outer reaches of our own solar system, but from the vast darkness between the stars, from another planetary system entirely, carrying with it perhaps the chemical signatures of alien worlds and the physical record of conditions in stellar neighborhoods we can barely imagine. The nickname interstellar ship emerged not from any serious scientific hypothesis about the object's nature, but rather from this deep-seated human tendency to anthropomorphize the unknown, to see in mysterious phenomena a reflection of our own technologies and ambitions. Yet there is something about this particular object that seems to invite such speculation more than most. Official agencies, meanwhile, remain cautious. The European Southern Observatory stated that it is too early to draw conclusions. The data still need verification. Even so, attention to the object is growing once again. If the signals are confirmed, this would mark the first sighting of the comet since its perihelion passage. The ESO's statement, released through their Public Information Office, emphasized the preliminary nature of all current observations and urged both the scientific community and the public to await more comprehensive analysis before drawing any firm conclusions about the nature and behavior of 3-Eye Atlas. They pointed out that observing conditions are challenging, with the object currently positioned at a relatively small angular distance from the Sun as seen from Earth, meaning it can only be glimpsed during the brief twilight periods at dawn or dusk. This geometry makes photometric measurements particularly difficult and increases the risk of systematic errors in the data. Nevertheless, the ESO has allocated telescope time on several of their premier facilities, including the Very Large Telescope in Chile, to conduct follow-up observations as weather and scheduling permit. NASA has also expressed interest, with administrators at the Jet Propulsion Laboratory confirming that they are exploring the possibility of redirecting certain space-based assets to observe the object, though they acknowledge that most spacecraft are not optimally positioned for such observations, and any reorientation would require careful planning to avoid compromising other mission objectives. For now, 3-Eye Atlas hides once more in the dawn light, as if watching us from afar, poised between myth and reality, between the stars and the unknown. Each morning before sunrise, as the sky begins to lighten in the east, the comet occupies a region of space that is simultaneously too bright for optimal observation, yet too dark for casual viewing. A liminal zone where only the most dedicated observers with the best equipment have any hope of catching a glimpse. This has created a kind of observational challenge that has captivated both professional and amateur astronomers worldwide. Social media platforms dedicated to astronomy have seen a surge in activity, with observers sharing tips on the best viewing times, the optimal equipment configurations, and their own attempts to image the elusive object. Some have succeeded in capturing faint smudges against the twilight gradient that might be 3-Eye Atlas, while others have documented their failures with good humor and renewed determination to try again the next clear morning. There is something deeply human about this collective effort, this shared pursuit of a glimpse of something that comes from beyond our cosmic neighborhood, and it speaks to the enduring power of the night sky to unite people across cultures, languages, and borders in a common endeavor of exploration and discovery. The story of 3I Atlas begins not with its recent reappearance, but with its initial discovery months ago, when the Atlas survey system first flagged an unusual moving object in its automated scans of the night sky. ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, was designed primarily to detect potentially hazardous asteroids that might pose a collision threat to Earth. But like many astronomical surveys, it has proven remarkably effective at discovering all manner of transient and moving phenomena. The object that would become known as 3I Atlas was immediately recognized as unusual because of its trajectory. Instead of following an elliptical orbit around the Sun like objects native to our solar system, it was moving on a hyperbolic path, one that would carry it into the inner solar system for a brief visit before slinging back out into interstellar space forever. This marked it as only the third confirmed interstellar object ever detected, following 1I Oumuamua in 2017 and 2I Borisov in 2019, where Oumuamua had been strange and inert, showing no signs of cometary activity despite its presumed icy composition, and where Borisov had been reassuringly normal in its behavior, closely resembling comets from our own Oort cloud. 3I Atlas seemed to occupy a middle ground, displaying some characteristics of each of its predecessors, while also exhibiting entirely new peculiarities that defied easy categorization. From the beginning, 3I Atlas attracted intense scientific interest. Telescopes around the world and in space were trained on the object as it fell inward toward its close encounter with the Sun. Researchers obtained spectra at various wavelengths, attempting to determine the composition of the nucleus and any surrounding coma or tail. They measured its light curve to understand its rotation state and shape. They searched for any signs of outgassing or fragmentation that might reveal the object's internal structure and stability. What they found was an object that seemed to shift its behavior as it approached the Sun, first appearing entirely inert like Oumuamua, then suddenly developing a faint coma as solar heating began to sublimate surface ices, then briefly intensifying in brightness before fading again in a pattern that seemed inconsistent with standard models of cometary activity. Some researchers proposed that the nucleus might have a heterogeneous surface, with regions of different compositions that became active at different temperatures and solar distances. Others suggested that the object might be spinning in a complex tumbling rotation that periodically exposed different faces to the Sun, creating the observed variations in activity. A few even wondered whether the object might consist of multiple components, perhaps a binary system, or a loosely bound cluster of fragments from some ancient collision in another star system, though imaging resolution was insufficient to confirm such speculation. As 3I Atlas approached perihelion, the point of closest approach to the Sun, anticipation grew. This would be the critical test of the object's structural integrity. Many comets do not survive their close encounters with our star, succumbing to the intense heating and tidal stresses that can tear apart loosely consolidated nuclei. The question of whether 3I Atlas would survive perihelion became the subject of friendly wagers among astronomers and intense scientific interest. If it survived intact, it would provide valuable information about the strength and composition of material formed in another planetary system. If it fragmented or disintegrated entirely, the manner and timing of its demise would still offer clues about its nature. As the predicted date of perihelion approached, observers prepared to maintain vigil through the critical period, though they knew that the geometry would be challenging, with the comet passing between Earth and the Sun, and thus being effectively unobservable for a period of days around closest approach. The plan was to observe the object as close to perihelion as possible before losing it in the solar glare, then to pick it up again on the other side, watching for any changes that might have occurred during its harrowing passage. Then came the silence. As Atlas emerged from behind the sun, it failed to appear where and when it was expected. Days passed with no detection. Observers began to worry that the object had indeed succumbed to solar heating, perhaps fragmenting into pieces too small to detect or sublimating entirely into gas and dust that quickly dispersed into space. The loss of an interstellar visitor before it could be fully characterized would be a significant blow to the field, a missed opportunity that might not come again for years or even decades. Some researchers began preparing papers analyzing the pre-perihelion data, attempting to extract whatever scientific value they could from an incomplete data set. Others held out hope that the object might still be there, perhaps much fainter than predicted, lurking just below the detection threshold of routine surveys, waiting for someone with the right equipment and determination to find it. There were suggestions that targeted searches be conducted using the predicted ephemeris to point sensitive instruments at the most likely positions, but telescope time is precious and competitive, and there was resistance to dedicating significant resources to what might prove to be a futile search for an object that no longer existed. For nearly a month, 3I Atlas remained lost, a mystery that spawned numerous theories and heated discussions in the literature and at conferences. Had it been destroyed completely? Had it fragmented into multiple pieces, each too faint to detect individually but collectively representing the scattered remnants of the original body? Had the trajectory calculations been somehow incorrect, causing observers to look in the wrong place? Or had something else happened, something unexpected that changed the object's brightness or trajectory in ways that standard models could not predict? This latter possibility, while seemingly far-fetched, gained some traction among those who had been puzzling over the object's peculiar behavior before perihelion. If 3I Atlas had already demonstrated anomalous characteristics, who was to say what other surprises it might have in store? The anonymous researcher from Atlas, who would later speak about the object's reappearance, was among those who continued to believe the comet might still be out there, and he had been conducting his own search efforts during whatever time he could secure on available telescopes, patiently working through the predicted positions and their surrounding regions, methodically ruling out areas where the object was not, while hoping to eventually find where it was. Then came Sunday night, and the faint signal that changed everything. The detection was not made by one of the world's premier observatories, but rather by a mid-sized research telescope conducting a routine survey, its automated detection algorithms flagging a faint-moving object in precisely the region where 3I Atlas was predicted to be, albeit much fainter than pre-perihelion brightness estimates had suggested. The astronomer on duty, initially skeptical that such a fortunate find could be genuine, nevertheless followed protocol and immediately requested confirmation observations from other facilities. Within hours, 2 additional telescopes had independently confirmed the detection, and by early morning, a preliminary orbit calculation based on the new positions showed excellent agreement with the predicted post-perihelion trajectory of 3I Atlas, accounting for gravitational perturbations and a reasonable estimate of non-gravitational forces. The object had survived perihelion after all, though apparently much diminished in brightness. either because it had shed considerable mass during its solar encounter, or because changes in its surface properties had altered its reflectivity. Either way, the interstellar visitor was back, and the race was on to characterize it before it faded beyond detection as it receded into the outer solar system on its way back to the stars. What makes the current observations so compelling and so perplexing is not just the fact that 3I Atlas has reappeared, but the nature of the signal it is producing. The rhythmic variations in brightness, initially noted by only one or two observers and dismissed by some as possible instrumental artifacts, have now been confirmed by multiple independent facilities using different instruments and different analysis techniques. The periodicity is real, repeating with a regularity that suggests a stable rotation or oscillation. What remains unclear is the physical mechanism responsible. If the object is rotating, as seems most likely, then the brightness variations must reflect significant asymmetries in either its shape or its surface properties, or both. One scenario that has been proposed involves a highly elongated nucleus, perhaps with an axis ratio of 3:1, or even more extreme, tumbling through space in a complex rotational state that causes different cross-sectional areas to be presented to both the Sun and to Earth at different times in the rotation cycle. When the long axis points generally toward us, we see a larger reflective surface, and the object appears brighter. When the short axis points toward us, we see less area and the object dims. The regular periodicity would then correspond to the rotation period of this tumbling body. However, this scenario, while plausible, does not fully explain all the observations. The spectral data, limited though they are given the object's faintness, suggest something more complex. During the brighter phases, the spectrum appears slightly different than during the dimmer phases, showing enhanced reflection in certain wavelength ranges that some interpreters have associated with smoother, more reflective surfaces. During dimmer phases, the spectrum more closely resembles that of typical cometary material, with the diffuse reflectance properties of rough, dusty ice. If these preliminary spectroscopic observations hold up under further scrutiny, they would suggest that the nucleus of 3I Atlas has a variegated surface with regions of distinctly different character. Perhaps one hemisphere or one end of the object is covered in relatively fresh, clean ice that reflects sunlight efficiently, while the other is mantled with a layer of dark, carbon-rich dust that absorbs most incoming radiation. Such heterogeneity is not unprecedented in solar system comets, where it is thought to arise from a combination of factors, including the initial composition of the material from which the comet formed, subsequent evolution due to radiation processing in interstellar space, and modification caused by repeated heating during passages through the inner parts of a planetary system. But 3I Atlas is not a solar system comet returning for another perihelion after countless previous passages. It is, almost certainly, making its first and only journey through the inner solar system, arriving from interstellar space with a pristine record of conditions in its birth system. The heterogeneity observed, if confirmed, would thus reflect conditions and processes entirely alien to our local cosmic neighborhood. The notion that the reflectance variations might be due to large metallic surfaces, mentioned by some experts, is one that most scientists are reluctant to endorse publicly, even as they may entertain it privately. The reason for this reluctance is obvious. Invoking metallic surfaces on an interstellar object inevitably invites speculation about artificial origins, and the scientific community remains deeply scarred by the Oumuamua controversy, during which serious scientific discussion was repeatedly derailed by sensationalistic claims about alien spacecraft that had little basis in the actual observational data. The lesson learned from that episode was that extraordinary claims require extraordinary evidence, and that even raising the possibility of non-natural explanations in the absence of truly compelling data serves mainly to attract unwanted attention from fringe theorists and to undermine public understanding of the rigorous evidentiary standards that science requires. Nevertheless, the reflectance properties of 3I Atlas during its bright phases are unusual, and several researchers have quietly noted that if one were to see such a spectral signature from a near-Earth asteroid, the natural interpretation would be that of metallic composition, perhaps an iron-nickel body similar to the cores of differentiated planetesimals that have been stripped of their rocky mantles by ancient collisions. Could 3I Atlas be such an object? A metal-rich fragment from a catastrophic collision in another solar system, ejected into interstellar space and now passing through our neighborhood? This would be extraordinary in its own right, requiring a specific and perhaps unlikely sequence of events. But it would at least be natural rather than artificial. The presence of cometary volatiles, evidenced by the faint coma observed before perihelion, complicates this picture, as pure metallic bodies should not outgas water and organics, but perhaps the object is a mixture, a metal core partially covered by ice and dust accreted during its journey through interstellar space, or retained from the protoplanetary disk where it originally formed. The timing of the brightness variations is another puzzle that observers are trying to understand. The 7.3-hour period, if that preliminary figure is correct, is longer than the rotation periods of most small solar system bodies, which typically rotate in a matter of hours, but it is not absurdly long. What is strange is how stable the period appears to be. Most tumbling bodies, especially those that are highly elongated and thus subject to strong torques from gravitational gradients and radiation pressure, exhibit complex rotational dynamics that cause their rotation periods to vary over time. Yet the limited data available so far suggest that 3I Atlas rotates with almost metronomic regularity, as if its spin state has somehow been stabilized. Some have suggested that the object might be in a relaxed principal axis rotation rather than a tumbling state, spinning smoothly around its axis of maximum moment of inertia, which would indeed produce very stable periodicity. But how would such a state be achieved and maintained? Most theories of small body dynamics suggest that tumbling should be the norm, with relaxed rotation states only emerging after significant energy dissipation through internal friction or other mechanisms. For an object making its first passage through the inner solar system with no prior thermal cycling to induce such evolution, the observed stability is somewhat surprising. Of course, much of this analysis is premature, based on only a handful of observations spanning less than a week. As more data accumulate, the picture may become clearer, or it may become more confused. That is the nature of frontier science, where each answer generates new questions and every measurement refines our understanding while simultaneously revealing new layers of complexity. The anonymous researcher from the Atlas Project, whose comments about the object's smooth, almost controlled motion have attracted so much attention, represents a fascinating case study in the tension between scientific caution and intellectual honesty. On one hand, he is clearly excited by what he is seeing in the data, excited enough to venture interpretations that push against the boundaries of conventional understanding. On the other hand, he has requested anonymity, perhaps recognizing that some of his statements could be misconstrued or taken out of context, used as ammunition by those who prefer sensationalism to careful analysis. In the leaked communication that has circulated among science journalists, he expands considerably on his public comments, describing in technical detail the trajectory analysis that has led him to question whether purely gravitational and standard non-gravitational forces can fully account for the observed path of 3I Atlas through the solar system. He presents calculations showing small but statistically significant residuals between the predicted and observed positions, residuals that persist even when sophisticated outgassing models are incorporated into the trajectory determination. He is careful to note that such residuals are not unprecedented, that trajectory modeling for active comets is notoriously difficult due to the complexity of the forces involved, and that there may be perfectly mundane explanations involving asymmetric outgassing from rotating nuclei or time-variable activity driven by the exposure of different surface regions. But he also notes that the pattern of residuals for 3I Atlas seems different from that typically encountered with solar system comets, more systematic and less stochastic. And he wonders aloud whether there might be some physical process at work that is not captured in current models. What exactly could produce such systematic trajectory modifications? One possibility, which the researcher mentions but does not endorse, is that 3I Atlas might have an unusually efficient rocket effect, with outgassing concentrated in specific directions that produces a net thrust capable of altering the orbit in measurable ways. If the nucleus is indeed highly elongated and rotating in a stable mode, and if active regions are preferentially located at or near the ends of the long axis, then the timing of outgassing relative to the rotation could produce a thrust that reinforces rather than averages out over multiple rotation cycles. This would be unusual, but not impossible. Another possibility is that the object's rotation state is not as stable as preliminary light curve analysis suggests, that there are subtle variations in spin rate or orientation that affect both the observed brightness and the direction and magnitude of non-gravitational forces in correlated ways. Disentangling these effects requires extensive observations over long-time baselines, observations that may be difficult to obtain given the object's fading brightness and increasingly unfavorable viewing geometry. A third possibility, which the researcher mentions only in passing and with multiple caveats, is that the trajectory modifications could be due to some form of torque or thrust that is not related to outgassing at all, but rather to some other physical process. He does not elaborate on what such a process might be, and it is perhaps this tantalizing vagueness that has fueled speculation in certain circles about the true nature of 3I Atlas. The invocation of ancient myths and the nickname Herald of the Void represent a different kind of response to the mystery, one rooted not in quantitative analysis, but in the symbolic and psychological dimensions of cosmic discovery. Throughout history, humans have told stories about the sky, weaving the movements of celestial objects into narratives that reflect earthly concerns and aspirations. Comets, with their sudden appearances and dramatic forms, have always occupied a special place in these narratives. They come unannounced, blaze across the heavens for a time, and then depart, leaving behind questions and memories. In an age when we understand comets as icy relics from the formation of planetary systems, as physical objects governed by Newton's laws and driven by the sublimation of volatile ices, there might seem to be little room left for myth. Yet the human need for narrative, for meaning, for connection between the cosmic and the personal persists. When an object arrives from another star system, when it exhibits puzzling behavior that challenges our models and understanding, when it disappears and then re-emerges as if by magic, it is perhaps inevitable that ancient patterns of thought reassert themselves. The Herald of the Void is not a scientific designation, but a poetic one, an attempt to capture in language the profound strangeness of this visitor and the uneasy feeling it provokes in some observers that they are witnessing something significant, something that transcends the mere addition of another data point to the astronomical catalogue. The reference to tales of celestial messengers returning from the void with news from other worlds draws on a rich tradition of mythological thought that spans many cultures. In Greek mythology, Hermes served as the messenger of the gods, crossing the boundary between the divine and mortal realms. In Norse tradition, ravens flew across the world gathering information for Odin. In numerous indigenous cultures, celestial phenomena were understood as communications from ancestors or spirits, messages that required interpretation by those with the proper knowledge. The modern scientific worldview ostensibly has no place for such thinking, replacing messages and messengers with physics and probability. Yet at the edges of our knowledge, where data are sparse and puzzles abound, the old narrative forms creep back in, not as literal belief, but as metaphor and frame, as a way of grappling with the unknown. When we say that 3i Atlas is a messenger from another world, we mean, of course, that it carries information in its composition, structure, and dynamics about the conditions in its birth system. We mean that by studying it carefully, we can learn about planet formation, stellar evolution, and the processes that eject material from one star system to send it wandering through the galaxy. But perhaps we also mean something more, something harder to articulate, about our place in a cosmos that is vastly larger and more diverse than our local experience, about the possibility of connection across the light years, about the question of whether we are alone or whether the universe is populated with other intelligences who might also gaze at passing visitors from foreign stars and wonder at their meaning. The phrase, disappearing in the fire of the sun, is particularly evocative, capturing the drama of the perihelion passage when 3i Atlas came closer to our star than Mercury ever does, subjected to temperatures and radiation intensities that would vaporize many materials and could easily destroy a loosely bound cometary nucleus. That it survived this trial by fire, if indeed it did survive intact rather than fragmenting into multiple pieces, speaks to a certain structural resilience. That it then vanished from view, hidden in the glare and geometry of the inner solar system, adds an element of mystery. And that it has now returned, faint but detectable, blinking its rhythmic signal across millions of kilometers of space, completes a narrative arc that feels almost intentional, almost orchestrated, though of course it is nothing more than the interplay of physics and geometry and the capabilities of our detection systems. Still, the feeling persists that there is something uncanny about the timing, something that invites interpretation beyond the purely physical. This is the power of narrative, the way that a sequence of events can create an impression of meaning and purpose, even when we know rationally that we are simply observing the deterministic evolution of a natural system. We are pattern-seeking creatures, evolved to find meaning in sequences, and when the universe presents us with a pattern as compelling as the disappearance and reappearance of an interstellar visitor, we cannot help but respond to it on both intellectual and emotional levels. The caution expressed by official agencies like the European Southern Observatory is entirely appropriate given the preliminary nature of the current data. Science progresses not through rushed announcements and premature conclusions, but through careful observation, rigorous analysis, and reproducible results. The history of astronomy is littered with discoveries that turned out to be artifacts, signals that vanished upon further investigation, patterns that dissolved into noise when subjected to proper statistical analysis. The scientific method is designed to filter out such false positives to ensure that the claims we make about nature are grounded in solid evidence rather than wishful thinking or instrumental error. This is especially important for high-profile objects like 3I Atlas, where public interest is intense and where any preliminary finding, no matter how carefully hedged with caveats, will be amplified and distorted as it propagates through media channels. The ESO's statement emphasizing the need for verification is not a cover-up or an attempt to suppress exciting findings, as conspiracy-minded observers sometimes suggest. Rather, it is a recognition of the responsibility that comes with making authoritative scientific pronouncements, a commitment to accuracy over speed, to truth over sensationalism. The fact that they are allocating telescope time for follow-up observations demonstrates that they take the initial detections seriously, that they believe there is something here worth investigating. But they are also managing expectations, reminding both scientists and the public that many preliminary signals fail to be confirmed and that patience is required as the observational and analytical process unfolds. The challenges of observing 3I Atlas in its current position cannot be overstated. The small angular distance from the Sun means that observations can only be conducted during twilight, when the sky is neither fully dark nor fully bright, creating a background against which faint objects are extremely difficult to detect. The low elevation above the horizon for many observatories introduces additional complications, forcing light to pass through more of Earth's atmosphere, which scatters and absorbs photons and introduces turbulence that degrades image quality. For spectroscopic observations, which require collecting enough light to spread into a spectrum and analyze the intensity at different wavelengths, the challenges are even greater, requiring long integration times that may be difficult to achieve during the limited windows of observable twilight. Space-based observations would avoid many of these problems, as telescopes in orbit can observe objects close to the Sun without atmospheric interference. But most space telescopes were not designed for such observations and have strict solar avoidance angles that prevent them from pointing too close to the Sun, lest their sensitive instruments be damaged by even scattered sunlight. The Hubble Space Telescope, for instance, has solar avoidance constraints that would likely prevent it from observing 3I Atlas in its current position. Other space assets, including various solar observing spacecraft, might have the right geometry but lack the sensitivity or spectral range needed to characterize the comet effectively. The James Webb Space Telescope could potentially make valuable observations, but its schedule is planned years in advance, and securing directors' discretionary time for target of opportunity observations requires a compelling case and rapid approval process. All of these practical considerations mean that even with widespread interest and recognition of the object's importance, obtaining high-quality observations is a significant challenge that will require careful coordination, favorable weather, and perhaps a bit of luck. The possibility that NASA might redirect certain space-based assets to observe 3I Atlas, mentioned by JPL administrators, is intriguing, but comes with its own set of complications. Most spacecraft are optimized for specific missions and have limited pointing flexibility. Redirecting a spacecraft to observe an unexpected target can disrupt planned observations, consume limited resources like fuel or power, and potentially compromise primary mission objectives. The decision to do so must balance the scientific value of observations of 3I Atlas against these costs and risks. For a flagship mission like JWST, the decision-making process involves input from multiple stakeholders, including the mission team, the science working groups, and the funding agencies. For smaller missions, the principal investigator typically has more authority to redirect the spacecraft, but may be reluctant to do so if it means sacrificing observations that have been planned for years. There are also technical constraints. Some spacecraft can only point in certain directions due to thermal requirements or communications geometry, and the speed with which a spacecraft can be repointed varies widely depending on its attitude control system. All of this means that while there may be considerable interest in observing 3I Atlas from space, actually making such observations happen is far from trivial. Nevertheless, given the rarity of interstellar visitors and the unique opportunity that 3I Atlas represents, it seems likely that some space-based observations will eventually be obtained, even if they are limited in scope or delayed in time compared to what would be ideal. The surge in activity on social media platforms dedicated to astronomy reflects the broader public fascination with the mystery of 3I Atlas. In an era when anyone with a decent telescope and CCD camera can contribute to astronomical observation, and when online communities allow rapid sharing of images, data, and analysis, major astronomical events become participatory in ways that were impossible in previous generations. Amateur astronomers around the world are attempting to observe the comet, comparing notes on equipment configurations, sharing ephemerides and finder charts, posting their successful and unsuccessful images, and engaging in spirited discussions about what the object might be and what the professional observations might ultimately reveal. This democratization of astronomy has both benefits and drawbacks. On the positive side, it engages the public in authentic scientific activity, builds understanding of the scientific process, and occasionally produces valuable data that complement professional observations. On the negative side, it can also propagate misinformation, amplify speculation beyond what the data warrant, and create echo chambers where extraordinary interpretations gain traction disconnected from the careful, skeptical analysis that characterizes professional science. The role of professional astronomers in this environment includes not just conducting observations and analysis, but also science communication, helping the public understand both what is known and what remains uncertain, pushing back against unfounded claims while remaining open to genuine surprises. It is a delicate balance, requiring both expertise and humility, confidence in the power of the scientific method, and recognition of the limits of current knowledge. The comparison of 3I Atlas to its two interstellar predecessors, Oumuamua and Borisov, is instructive for understanding why the current object generates such intense interest. Oumuamua burst onto the scene in 2017 as a complete surprise, the first confirmed object from interstellar space ever detected passing through the solar system. Its discovery was partly a matter of luck, as the object was already receding from the Sun when first detected, and was only visible for a brief period before fading beyond detection. What made Oumuamua extraordinary was not just its interstellar origin, but its bizarre properties, an extreme elongation inferred from its dramatic brightness variations, a lack of any detectable cometary activity despite the heating it must have experienced during its close solar pass, and a small but definite non-gravitational acceleration as it receded from the solar system that could not be easily explained by standard outgassing models given the lack of visible coma or tail. This combination of properties led to intense speculation about the object's nature, with proposals ranging from mundane explanations involving unusual comet compositions or geometries to exotic scenarios involving nitrogen icebergs or hydrogen-rich material, to the controversial suggestion by some researchers that the object might be artificial, a piece of technology from an alien civilization. The debate over Oumuamua became contentious and somewhat toxic, with the scientific community dividing into camps that sometimes talked past each other rather than engaging constructively. The lesson many took from this episode was that interstellar objects could be far stranger than anticipated, and that our theories for solar system comets and asteroids might not apply straightforwardly to visitors from other stellar neighborhoods. Comet Borisov, discovered in 2019, represented in many ways the opposite experience. Here was an interstellar visitor that looked and acted exactly like what astronomers expected a comet to look like and act. A bright nucleus surrounded by an extensive coma and a tail, spectroscopic signatures consistent with water ice and carbon-based molecules, outgassing behavior that matched standard models, and even fragmentation near perihelion of the sort that is commonly observed for solar system comets under thermal stress. Borisov was reassuring precisely because it was normal, demonstrating that at least some interstellar objects behave like their solar system counterparts and suggesting that planet formation processes might be similar across different stellar systems. The extensive observations of Borisov, obtained by dozens of telescopes over many months, provided the most detailed characterization of an interstellar object to date and confirmed that, at least in this case, there were no major surprises lurking beneath the surface. Some astronomers were almost disappointed by Borisov's normalcy, having hoped for exotic compositions or bizarre phenomena that might reveal fundamental differences between our solar system and others. But the object's very normalcy was itself a significant scientific result, constraining theories of planetary system formation and evolution.